We're now going to introduce some architectures that are different from the typical von Neumann architecture. Now, the von Neumann architecture has served the field very well for over 60 years, but now we're starting to see problems that are a lot larger in size and complexity since when the architecture first came out. I mean, think about the problems that we face nowadays. They're much larger and more complex than the types of problems that were being encountered back in the 1940s. And because of this, there are some computer scientists who believe that the von Neumann architecture may be reaching the end of its useful life. Part of that is because of the rate of increase in the number of instructions that are being computed. While things are a lot faster than they were 60 years ago, and we're still developing faster and faster machines, the rate of that increase in speed is slowing down. So while machines are getting faster, the rate of increase in speed is not as much as it used to be. And there are some physical limitations as to why this is happening. I mean, when we're designing the components of the architecture, for instance, I mean, we can only place gates so close together on a chip. I mean, we can make them smaller and smaller and try to move the gates as close as we can and when we embed or etch the chip, I should say, but we can't really overlap them. We can't stack them on top of each other, at least not yet. So we can't get them any closer. And then also you have to consider the electronic signals. There are limitations to this. They can't go any faster than the speed of light. And while the speed of light is really, really fast, but we can't go any faster than that. So we do have limitations for this. And this type of problem is what we call the von Neumann bottleneck. To solve this problem, computer engineers are rethinking many of the fundamental ideas that we've been talking about so far about the von Neumann architecture. And they're studying different approaches or non-traditional approaches to computer organization. And these types of approaches are what we call non-von Neumann architectures. Basically, they're asking themselves the question, is there a different way to design and build computers that can solve problems 10 or 100 or even 1,000 times larger than what can be handled by today's computers? And fortunately, believe it or not, the answer to that question is yes, there is a different way. One of the most important areas of research in these non-von Neumann architectures is based on the following fairly obvious principle. If you cannot build something to work twice as fast, build it to do two things at once. The results will be identical. So from this comes the principle of parallel processing, or sometimes called parallel programming. The idea with this is we're building computers not with just one processor, but we're building them with tens or hundreds or even thousands of processors. So if we can keep each processor occupied with meaningful work, then it should be possible to speed up the solution to large problems by 1 or 2 or even 3 orders of magnitude, and we can overcome the von Neumann bottleneck. So the whole point here is that we're going to have all these processors that do some work on different parts of the problem at the same time. So instead of having one processor doing one step at a time, if we can take a problem and break it down into parts and work on all of them simultaneously, then we can solve the problem a lot faster because we can complete several things at once. And this is actually the idea behind the dual-core and quad-core processors that have 2 or 4 separate processors on a single chip. So most machines are now having 2 or 4 processors in a particular computer chip. We're now even starting to see CPUs that have 8 or even 16 cores. So we're already getting to that trend where we can have several things going on at the same time. The approach for placing multiple processors on a single chip is fine for a small number of processors, say 2, 4, or 8. However, we need a completely different approach to build large-scale parallel systems that contain hundreds or even thousands of processors. So there are two fundamentally distinct approaches for designing these massively parallel systems. The first technique is termed SIMD parallel processing, and the second technique is termed MIMD parallel processing. So we'll talk about both models in more detail. The SIMD stands for Single Instruction Stream, Multiple Data Stream. And in this model, we have a single program whose instructions are fetched, decoded, and executed in a sequential manner by a control unit. However, the ALU, which we're talking about the circuits and the registers, they are replicated many times. And each ALU is going to have its own local memory where it may keep private data. So when the control unit fetches an instruction, such as a load, an add, or a store, and so forth, it's going to broadcast that instruction to every ALU, which then executes the instruction in parallel on its own local data. So, like for example, if we have 100 replicated ALUs, we can perform 100 parallel additions by having every ALU simultaneously execute the instruction. Here is an illustration that gives us a model of the SIMD architecture. So the idea is that we have this one control unit, and it's going to broadcast the instruction to all of the ALUs simultaneously, and each ALU would have its own memory. So a good example of how this would be used is, let's say I have this set of numbers, and maybe I want to add one to it. Normally, we would just have to go to each number one at a time and add one to it. But that can take a while, especially if this set of numbers is very large. With the SIMD architecture, what we can do is take each item of the set and send it to its own individual ALU and memory, and then we would add one to all the numbers simultaneously. MIMD stands for Multiple Instruction Stream, Multiple Data Stream. Sometimes this is also called cluster computing. It's actually a more interesting and a more widely used form of parallelism. So in this approach, we actually replicate entire processors rather than just the ALU. And every processor is capable of executing its own separate program in its own separate memory, so its own separate private memory, at its own rate. Now, each processor memory pair is a von Neumann machine. So, I mean, it could be a processor board of some type, it could be a complete computer system, like a desktop machine or a laptop, but each system is executing its own program, and it has its own private memory, and it can run things at its own pace. However, the trick is, instead of having to solve the entire problem by itself, like what SIMD does, what happens here is that the problem is solved in a parallel fashion by all processors simultaneously. So each processor will tackle a small portion of the overall problem, and then it's going to communicate its result to the other processors by using an interconnection network. And this is simply a communication system that allows processors to exchange messages and data. So here is a diagram illustrating the MIMD architecture. So we have the processors and separate memories that are just kind of dispersed around, but they're connected with each other with this interconnection network. So we can actually exchange data, we can exchange results. It's not the case that we have one machine that is like the central core unit that sends all the instructions to all the other processors. Instead, we may have one of these processors send out parts of problems to the other processors while that processor does a portion itself, and then all the results get combined together to get the actual result. So for example, let's think about our phone directory search example that we talked about a couple times. Maybe we have 20 million entries that we need to search. Doing that sequentially would take a while. So what we can do instead is divide portions of that directory to each processor. So each processor will only have to do a very small fraction of searching that directory, and then they're all going to do that computation, and one of them should say that this name has been found, or if the name doesn't exist, it's just none of them are going to say that the name has been found, but it's a way that we can speed up searching the entire directory.